Hello everyone, my name is Avant Mehta and today I'm recording for the last lab of ABE425 Lab 11, and that's PID Control app. So first we'll have a very quick overview of the basics of PID Control. We have a set point, that is a target value we're trying to reach. We have a PID controller, that's proportional, integrative and derivative controller. That gives an output which goes to the process, and that takes into account the disturbances, the external fluctuations that we can't really control or noise. And along with the process variable is the output of this, but it has a feedback which goes back to the sensor. In today's lab, as you can see, we're using a light dependent resistor which is placed just next to the LED bulb, and that is the sensor which gives out the measure process variable back into the PID controller, and that's our feedback loop. So that being said, I have to go through some questions and some demonstrations for the day for this PID controller. But first I'll show you my app. We have the actual value, which is the instantaneous current value that it is right now. We have the error, which is the difference between the instantaneous value, the actual value, and what the set point value is. Our set point value over here, I should first cover, ranges from about 0.9 till 3, and that happens through our calibration that we did in the beginning, where we first set the value of the bulb, the pulse width modulation, to be 5 so that we get its max value, and the lower calibration where we set the PWM to be 0 to the LED so that we calibrate and see what the range of values of output that the set points can possibly be. Then we have our error int, and that repeatedly gets calculated iteratively by doing error int equals error int plus the error that's currently there for the current iteration, and that links to our ki value, as we are going to see. And then we have the error diff value, which represents the difference in the error between the error of the current iteration and the previous iteration. And then we have the pulse width modulation output. All of these are measured in volts, by the way, and that tells us what is being outputted by my yellow wire into the light bulb over here in my circuit. And the way I design my app is that for all these values, it'll update the gauge value as well as the numeric field output value for all these 5. And then we have the controls for Kp, Ki, and Kd. Again, these are the proportional, integrative, and derivative coefficients. And the slider over here is for a set point, which is currently at 1.307. And then I have my N counter that actually just represents the number of data points it's taken thus far, and the num samples is what controls the value of N, that is how many values of samples it's going to take every time it has to calculate the next iteration for PID control. So first, I'm going to demonstrate that the controller responds to a change in the set point, and it's currently again 1.307, but I'm going to change it to be it is 1.3. I'm going to make it 1.7. And what I'm also going to do is I'm going to change the number of samples to be about 4 or 5 so that it does not take that much time to get that done. And as I come close towards that, I can make it update more frequently by changing the value of my num samples. And as you can see, I targeted a set point value of about 1.7, and I did get an actual value of about 1.7, and the error is within 0.01 plus or minus from 0. And these values are also stable. All the error diffs and the error int, the error is very close to 0, and the actual value is very close to what we targeted the set point. Next is demonstrate that the set point is not reached when you do not have an integral action that is set Ki to 0, but you do have a proportional gain, give Kp a stable value. So I'm going to try and set my Kp to be as close as I can to 0. And I'll change my target value to be like 2. And as you can see, the set point value is not actually achieved. Let me set this back to a decent value because my error int became too high. It became 23, 24. So that is why it cannot reach the set point value when my integral action is not being affected because my ki was 0. Now let me try to get this back into control. I typically do that by just changing my num samples to be reasonably high, and as it comes close to my error int being 0, I just reduce my num samples back down to 1 so that it updates pretty quickly. Oops. And again, we're back in control. My error int will now not exceed 0.15, which means we're in control. Everything else is also still in control with my new target value, which was 2.015. So that's the second check we've done. And now demonstrate how the output becomes unstable if you set the values of Kp, Ki, and Kd too high. Observe your gauges and your LED. So let's set the Kp to be about 6, my Kp to be like 3, and my Kd about 5. So as you can see on the top right of your screen where you're looking at the actual circuit, it toggles between an output value of 0 and 5 far too often. So you're not seeing a very consistently on LED, but you're seeing it flash back and forth. Every time a new iteration is done, it's repeatedly going very high on and then off repeatedly. And that's an unstable state. So that's what happens when the Kp, Ki, and Kd are too high. So I'm going to try and get it back into control by making this value about 1 and this about 2 and this about 2. And also setting this to be about 4 until I reach the point where it's about stable, and then bringing it back down to 1. I think I'm stable, yeah. Now demonstrate how your program reacts to external disturbances. Cover or uncover the light dependent resistor. So for that I'm going to use this numpad over here, which simply acts as an opaque object, which I'm going to place between my light dependent resistor and my bulb. So that way there's no feedback happening between the LDR and my bulb, so it acts as a disturbance. And the whole idea is that it'll temporarily go out of control when there's no feedback, but it'll find its way back to being stable. So let me position that over here. As you can see, my PWM went pretty high. My error was high, it went up to about 0.15, I do believe. But once the disturbance was no longer there, I took this numpad away. We're back into control again. So that shows how the PID controller takes into account what's happening with the external disturbances. And once it, well, first of all, if there was some fluctuation happening in the environment, it'll take that into account as it's doing its feedback. And secondly, even if it temporarily loses its feedback effect because there's no more close contact between the LDR and the bulb, once that disturbance is entirely removed, we come back into stable control. So that's a plus point of PID control. Now, unfortunately, I was not able to get the plots working to show all the error values, the actual values, and the error ints and the error diffs as we went from 0 till 10,000 samples, but I tried to compensate for that by showing what happens on the gauges and the values on my screen. So that being said, I hope that you were able to learn something about PID from here, or at least further your knowledge in PID if there was something I was able to tell you that you didn't already know. And as always, for the very last time for ABE425 Labs, thank you so much for watching my video and have a good one.